Welcome to the class on obtaining discrete time transfer function. Discrete time transfer function occurs in discrete systems, and that is the main difference from continuous time transfer function, because still, when we talk about transfer function, we mean linear systems. I hope that today's topics will be relatively pleasant for you, because the calculations will not require any advanced mathematics. Well, maybe apart from invariant methods. However, something for something. Today we will discuss 10 different methods of obtaining discrete time transfer function, and I warn you in advance that the solution method will be indicated, and therefore you will have to learn all methods. First, invariant methods, and the first one is step-invariant method. Please do not learn the upper formula. More important is the ability to perform the subsequent steps. And what do we need to calculate one by one? First, the step response of the object, for which we want to obtain the transfer function. Then we need to write the obtained function in discrete time. Here is a simple substitution. And then we need to calculate the Laurent transform of this response in discrete time. At the very bottom, I presented how the physical system should be constructed to obtain the transfer function using this method. These elements with TP are so-called pulsars, and the block on the left is a zero-order Holt extrapolator. The second method is the impulse-invariant method. The calculation method is very similar. That is, we need to calculate the impulse response and then calculate the Laurent transformation from its discrete form. There is also a small difference in the last formula. In the case of the step-invariant method, this Laurent transform was multiplied times 1 minus z to the power of minus 1, which, in discrete systems, is differentiation. That is the letter S in continuous time systems. Please remember now the unit step transform from previous classes. 1 by 1 minus z to the power of minus 1. And the Laplace transform of a unit step? 1 by S. By associating in this way, many expressions seem more obvious. The next three methods belong to the easiest group of methods, in which the only thing you need to do is substitute the appropriate formula. In each method, we substitute a different formula for the variable s, so the obtained discrete time transfer function will also be different. But the only difficulty in these methods is remembering the formula and representing the result in the form indicated in the task. Almost always the result on one fraction line and segregated by powers of z. The subscript next to the letter G indicates the method used, but this notation does not have to be used. I say it almost always because in pole zero matching methods there will be no such requirement about result form. On the contrary, I will be grateful for the result not segregated and not on one fraction line. We can see that this method is a little more complicated than the previous ones, but this is only at first glance, because in practice these methods are the simplest. I have written here a 4-step algorithm for obtaining the transfer function, but the first 3 steps consisting in mapping the poles and zeros of the transfer function g of s to the transfer function g of z. If we have a pole with a value of, for example, minus 3, then in the discrete time transfer function, this pole will have the value e to the power of minus 3 tp. Zeros should be calculated in a similar way. In the third step, something like infinite zero appears. In practice, you should put the expression z plus 1 in the numerator, and it should be raised to the appropriate power. to which this depends on the method. In the first method, m minus l, and in the second method, it is one less. I assume that m is the denominator order and l is the numerator order. The last step is the gain calculation. The last group of methods is finite difference methods. These methods require a differential equation, so one needs to write it first. Then, using an appropriate method, one needs to convert the differential equation into a difference equation. And the last step is transformation from the difference equation to the discrete time transfer function. Individual methods differ only in how we approximate the derivative at a given point. We are interested in the first three presented methods. At the very bottom, I only show that the methods from this group may be more complicated. If there is a need to calculate higher derivatives, then each of the terms in numerator also needs to be approximated with the given expression. I very briefly presented 10 different methods for obtaining discrete time transfer function, but why are there so many of them? How do they differ? They certainly differ in the difficulty with which they are obtained. The most convenient will certainly be the substitution methods, and the best, the one with the shortest formula. Invariant methods seem to be the most difficult. The second difference is rather an indication on one exception. In the case of the impulse-invariant method, the object gain obtained is different than in all other methods. The third difference is quite obvious. Well, since we have 9 methods leading to different transfer functions, it follows that these objects will have different dynamics. The last difference is probably the most important, because as a result of obtaining a discrete time transfer function, we may lose information about the stability of the object. For example, using the delta backward method, unstable object can be turned into a stable object, and using the delta forward method, a stable object can be transformed into unstable object. Fortunately, the solution here is to use an appropriately small sampling time TP. However, methods that provide retention of information about object stability are the Tustin method and invariant methods. Finite difference methods do not retain information about the stability. And I don't know what it looks like in the case of the pole zero matching methods. I have never checked it and I don't want to guess. Okay, we have already done the theoretical introduction. Now let's practice individual methods on specific examples. Let's start with something simple. The task is to obtain the discrete time transfer function of the object using the step-invariant method. First, we need to calculate the step response of this object. I assume that you are already familiar with these issues, and I will not describe them in detail. There is no need to write all this. I wrote this the first time to remind you how it worked. Now we need to determine a discrete function in the time domain. We simply substitute ntp for the variable t. This subscript si does not need to be written, but the variable z in brackets does. I remind people who have already taken classes with me, and I inform the rest, that when we use only a capital letter, we assume that it depends on the complex variable s, and when we use only a lowercase letter, we assume that it depends on time t. The transform of the sum is equal to the sum of the transforms. The Laurent transform was covered in the previous classes, so I assume that you already know how to calculate it all. And we need to reduce the result to one fraction line and segregate it by the variable z. And this is the final form of the result. I treat 3/5 as one number. There is no stored fraction here, because one could just easily write this number as 0.6. Now assume that the transfer function is given. Again, we use the step-invariant method. We perform the calculations in the same way as before. And one more task related to the step-invariant method. Let the object transfer function be equal to Here I would like to remind you that in the case of a delay, we first perform calculations for the non-delayed function, and finally, when we have the appropriate result, we apply the substitution. We calculated this in the previous task, only with number 2, and we multiply it times the unit step. It is not necessary here, but so as not to forget about it later. And wherever time has appeared, we now need to substitute t minus 4. If a specific sampling time Tp is given in the text of the task, it should be substituted at the beginning or end of the calculations. And if no specific value has been given, we leave such a fraction. It may also happen that the delay will have Tp at the beginning, and then it will shorten at this point. Z variables need to be multiplied. Now let's move on to the impulse-invariant method. Let's calculate the discrete time transfer function based on the object model Now we need to calculate the impulse response. Let me remind you that to use the residual method, the degree of numerator must be smaller than the degree of denominator. This is not met here, so it needs to be transformed first. Of course, there are different ways to break it into two parts. You can use any one. Please do not omit the parameter for Dirac delta. Theoretically, the Dirac delta equals infinity, so when multiplying by any value, we should get the same thing. But by changing this parameter at this stage, we would obtain a different final result. So please stay with the parameter received in the calculations. If we want, we can base on integers. We remain with the impulse-invariant method. Here is the derivative of the product. Please note that we have two properties here, that is, change in the complex scale z and multiplication by n. It's a good idea to either calculate it on the side or go straight to the result, but be very careful not to make a mistake. Calculating the derivative would be more difficult, so I will start with the NTP function. And wherever there is z, I need to substitute e to the appropriate power. And this is the last task from the impulse-invariant method. We need to know where the poles are. We solve it in a standard way, as for complex poles. If we don't remember the properties of the trigonometric function, we can simply draw it. We see that the sine of a negative angle is equal to the sine of a positive angle, but with the opposite sign. If one needs to calculate the Laurent transform of a trigonometric function, it will be given. If the value of Tp were given, the sine and cosine would have to be calculated, similarly to e to the power, and then we would multiply all these numbers to obtain specific parameters with subsequent powers of z, and similarly in other tasks and other methods. If the Tp value is given, it should not only be substituted into the result, but also calculated. Let's now move on to the next group of methods, substitution methods. For an object described by transfer function determine the discrete time transfer function using Tustin method. With this method, we only need to remember the appropriate formula, and don't make a mistake in calculations. We substitute this expression for each variable s. In my opinion, the easiest way is to shorten both denominators, but everyone can choose their own path to the result. Both denominators are identical, so they can be shortened. The result in this form is not correct for me, because z to the 0 power is in two places in both numerator and denominator. Three terms should be next to each other. Let's do the calculations for the same transfer function. But using the delta minus method or delta backward method. Of course, you don't have to write this formula in that way every time. You can immediately substitute this expression. Each substitution method is basically the same, so I will not present the delta forward method. In this task, we will use the pole zero matching method. Let's take the same object transfer function again. Let's start with the first method, that is with mapping m minus l infinite zeros. First of all, it's a good idea to enter the gain so as not to forget about it. You can use the symbol k alone. I only wrote this subscript in association with the method. Let's start with the poles. There are two poles in the origin transfer function, 0 and minus 2. Therefore, we need to map both of these poles in our new transfer function g of z. First, the minus 2 pole. According to the formula given earlier, the pole should be the value e to the power of tp times the pole. That is, in our case, The second pole is 0, so e to the power of 0 is of course 1, but I wrote it so that everyone can see where it came from. Now we move on to the zeros. Our original transfer function has one zero in the value of minus 1/3. So but we also need to add the so-called infinite zeros, specifically m minus l such zeros. That is, the difference in degrees of denominator and numerator, which here is 1. So we have to add 1 0 exactly at minus 1. Our discrete time transfer function is almost ready. We just need to calculate the gain. For this purpose, we equate both transfer functions, substituting 1 for z and 0 for s. And again, the ones on the left and right are completely unnecessary. I added them for better readability. Here we have a situation where, in both cases, there is a 0 in denominator. This is caused by integration in the object, and these zeros should simply be shortened. And then we need to obtain the kpz value. And this gain just needs to be substituted into the transfer function. And please do not transform it further. For these methods, please leave the result in this form. Let the gain be in such a stored fraction, and let the whole remain unmultiplied. It will make it easier for me to check tasks. Now let's consider a slightly different continuous transfer function. And let's perform calculations for both. The first method with pole zero matching, that is with m minus l infinite zeros, as well as for the second method, that is with m minus L minus 1 infinite zeros. First method first. M minus L in this problem is 0, so we don't add any infinite zero. We still need to calculate the gain. Again, we have the case that there is 0 on both sides of the equation, this time in numerator. This is due to differentiation in the original transfer function. These zeros should be shortened, and we calculate kpz. And substitution. Let's move on to the second method. The poles and zeros are, of course, in the same places, so one could just rewrite from the previous method. But please count how many infinite zeros should we add. M minus L minus 1 equals minus 1, which means that the discrete time transfer function cannot be obtained using this method. We only have one group of methods left, finite difference methods. Let's again consider the transfer function previously used. And we will perform the calculations using the backward finite difference method. That is, we will use the approximation finite difference methods assume that we have a differential equation available. If it is not given in the text of the task, then such a differential equation must first be obtained from the available transfer function. How? This has already been said, so I just remind you that the transfer function is the ratio of output to input. This should be multiplied diagonally. Then the inverse Laplace transformation should be performed on both sides. All these variables depend on time t, so there is no need to write it. Just be careful to use lowercase letters here. And now one needs to apply the substitution according to the selected method. If we have a pure variable u or y without a derivative, we substitute exactly the same variable depending on step n. If we have the first derivative, we use the substitution that results from the given method. But we have the second derivative here, so we just need to calculate what to substitute for the second derivative. Here, of course, we use this notation conventionally, because the time derivative of the value is 0, but here we use such a conventional substitution. In both of these derivatives, we need to use exactly the same substitution, but paying attention to the argument. And here we have everything we need to perform the substitution for the differential equation. I also anticipate questions in advance. In the case of these entries, we cannot omit the dependence on n. These brackets with arguments must be written each time. Now we need to transform this equation appropriately to finally obtain the discrete time transfer function, that is, the quotient y of z to u of z. First, let's get rid of the fractional lines by multiplying by tp to the second power. Now please pull out the variables with the same argument in front of the brackets. And now we need to apply the Laurent transformation on both sides. The signal delay is expressed by z to the appropriate power. All that remains is to determine the transfer function. And we have the result in the form of discrete time transfer function. Does this result remind you of anything? Please compare this result with the result of using the delta backward method. Do you see this? In both cases, we got the same result. The backward finite difference method and the delta backward method are actually the same method. Similarly, the delta forward method and the forward finite difference method. So why are there two separate methods? Because it depends on what we start with and what we want to receive. If the starting point is a differential equation and we need a difference equation, it will be more convenient to use finite difference methods. If the starting point is a continuous transfer function and we want to obtain a discrete time transfer function, it will be more convenient to use the substitution methods. Let's calculate one more task for the same transfer function as before. And using the central finite difference method. The approximation sign is very important here because an equal sign would be an error. A differential equation, if one can calculate it in his head, can be written directly. Approximations to the higher derivatives of functions can be memorized and simply substituted, but the time on task will involve deriving these formulas. At this point, you can also go straight to writing the transfer function, but please take into account that if you make a mistake, the more calculations you miss, the more I will subtract for such error. Of course, we can multiply numerator and denominator times z to the second power or times z to the power of -2. It depends on what transfer function we want to obtain. and in subsequent topics it may be different. In any case, I assume that the transition from positive to negative powers, or from negative to positive powers, is not a problem for you. This two-sample shift back could also be done at the difference equation stage. It could simply be rewritten by reducing each argument by 2. The central finite difference method is not the equivalent of Tustin method, but you can calculate what should be the substitution formula to obtain the same result. Let's say that every year the first person which send me solution, with calculations for both methods for an example, will receive 2 bonus points. Let the solution immediately provide transfer function with negative powers of z. And that's all I wanted to show you during these classes. Thank you for your attention and have a nice day.